Okay, so let's get started. We are back after the midterm. Hopefully that went well. The grades are already out. So if you have any comments or concerns, please let me know. We're gonna now move to a different class of neural networks. We've been talking about how to improve training and also how to evaluate neural networks in the last couple of lectures. But starting from today, we're going to see different versions or architectures that can help us process different types of data. And we're going to start with convolutional neural networks. As usual, some announcements. The first submission of the final project, which is the project proposal, the deadline has been extended to this Friday, which is October the 18th, also 11:59. And according to our schedule, we should have another programming assignment out by today, but I'm going to just delay that as well. So the convolutional neural network assignment is going to come out on Friday probably, so you guys have more time to work on the proposals. Also, I'm considering to change the style of the assignment a little bit based on the feedback I got from you. By the way, if you haven't filled out the form to evaluate the course yet, please go ahead and do it if you have time. It's not mandatory. I'm not going to give you any points for that. It's just for me to get to know how you are experiencing this course and if I need to make any changes to it. So I got some interesting comments about the assignment. Maybe I'm considering to change it a little bit for this next one. And yeah, as I already mentioned, last time we were talking about mini-batch gradient descent. So these advanced optimization algorithms that make training faster, especially in large data set regimes. We talked about mini-batch gradient descent, which is this idea of using mini-batches or chunks of the data set to update our weights more often in a given epoch instead of just updating it once. And then we saw 3 different algorithms to speed up the mini-batch gradient descent, which is gradient descent with momentum, RMS prop, and Adam. So for today, as I said, we have a lot to talk about. First, I'm going to motivate convolutional neural networks from this perspective of the number of parameters that you have in a neural network when we are dealing with images. Then we have to define what filters are to define what convolutions are. And then we're going to see different types of convolutions, padding and strided convolutions, or convolutions with padding and strided convolutions. Then we're going to see convolutions over volumes, how to put padding layers in your network, and at the end we're going to see a full convolutional neural network for image classification. So to motivate convolutional neural networks, we have to think about the number of parameters that we need to process a given image. Using the things we know so far, like multi-layer perceptrons, if you try to use them to process images, which we have done in both the programming 1 and programming 2 assignments, we will see that as the size of the image grows, we have an explosion of the number of parameters in our network. So let me show you this with an example. Consider this image, which is 1,000 pixels in height and 1,000 pixels wide. So it's a squared image that is a high definition image, but even for like today's standards, is not actually a very large image. But if you want to process that image with a multi-layer perceptron, what you have to do is you have to stretch that image into a single vector, right? Which in this case would have how many dimensions, right? This is a very easy computation to do. You just have to multiply height by width by 3, and by 3 because we're talking about a colored image, so you have 3 channels in there, right? You have red, green, and blue. So that gives us 3 million dimensions, right? And this is not even a big image, as I said. And this is the size of the input, right? That X vector there would have 3 million inputs, or 3 million dimensions. So if we define a hidden layer, or this is our first hidden layer here, right? And the size of that hidden layer is N1. Remember the superscript square brackets 1. That number there defines the index of the layer. We always start the input layer with 0. So our first hidden layer has 1,000 neurons. If that's just, just for the sake of the argument here. Then our weight matrix for that layer would be of the shape N1, N0, right? So we're going to have 1,000, a matrix would be 1,000 rows by 3 million columns. Okay? That would lead to 3 billion parameters in only one single layer, right? So, and we are not even talking about a very large hidden layer, okay? So we have problems. First is the most obvious one is computational resources, right? We would have to load all these matrices in memory, and they are very large matrices, and you have to process them using some sort of processor, maybe hopefully a GPU. So fitting these matrices in memory would be computationally intensive, right? That's a practical problem, but a more theoretical problem is we're going to need a lot of data to avoid overfit because there's too many parameters. Okay. So it's not a very good idea to use MLPs for computer vision, especially if you want to deal with large images, which is normally the case, right? That's what we want. And we don't want to be limited to the size of images we want to deal with, right? Ideally, we would like to work with images of any size. So that's the main motivation for convolutional neural networks, is to somehow detach the number of parameters of our neural networks from the size of the image. Right now, the number of parameters we have, they are proportional to the size of the image, and we don't want that. Right? So that's what we're going to have. We're going to try to solve with convolutions here. So that's exactly what I said, right? We can use convolutions to process large images with a constant number of parameters, and hopefully by the end of the lecture, you will be convinced by that. Okay. And what are convolutions then? So convolutions are operations for now. I'm going to define them more formally in a minute. But they are operations to apply filters. And again, now I have to define filters, and I'm going to do that first. Filters are transformations to the image. And I'm sure you've seen this because probably most of you use Instagram or some other like social media app like that. And you apply like filters to your videos very frequently probably. And filter is what you imagine, is a transformation to the original image. And a very common filter is the blurring filter, which takes the original image and just makes it blurry. What we're going to do with convolutions is applying these filters. How do you represent a filter? A filter is typically a small matrix, like that one. Oh, sorry, it's not there yet. But it's typically a small matrix of weights. So what you see here on the left-hand side is a very small image that is 5 by 5. And I'm highlighting just one pixel of that image of value 161, and not only that pixel, but its neighbors. So I'm focusing on that central pixel there, 161, and the other pixels you see, they are colors, right? I'm assuming a values from 0 to 255, okay? So 0 would be dark and 255 would be white. And this is just a black and white image for now, okay? So we have that central pixel there and its neighbors. Okay? And a filter, as I mentioned, is this small matrix that we're going to somehow apply to that pixel. And when I say applying here, I'm denoting application by that symbol multiplication. So, and you will see why. Again, it's a small matrix of weights. So the values you see inside the filter there, namely 0.0625, 0.125, 0.0625, 0.125, 0.25, these 9 values you see there, you can call them weights. And why? Because the way we apply filters is by multiplying each weight by its respective pixel values in the image. So formally, here is a 3x3 filter, right? So what you're going to do is here, to apply this filter, by multiplying each weight by its respective pixel value. So I, J, and the formula is M, I, J times K, I, J. Mij is the pixel value and Kij is the weight value. So for that example there, we would have these result, 0.0625, and I'm going to apply this very first weight here to these 206 pixel, right? Plus 0.125 times 0.125 times 205 plus 0.0625 times 247 plus, you got the idea, right? 0.125 times 144. Just to complete till the center, 0.25 times 161, and so on. And we don't have to do this math by hand. I already did it for you. That would give us 178. Okay? So by applying this filter to that particular central pixel, I transformed that pixel from 161 to 178. The neighbors haven't changed. The neighbors are the same. I only changed the central pixel. And I changed this pixel by looking at its neighbors and multiplying them by a given set of weights. And this is a given set of weights. I came up with these numbers, okay, by hand. And magically, what they do is actually blurring the image. So somebody actually figured that out. So if you use those combinations of numbers, you would get a blurry image if you apply this to every pixel in your image. But now that we know what filters are, which are just weights, but they are disposed in a matrix, we can define convolutions. And convolutions, the idea of convolution comes from math and is a way to operate with functions. We are not going to discuss that math here. And in computer vision and image processing, when you talk about convolution, we are talking about applying a filter to an entire image. That's it. Okay, so we know how to apply a filter already to one pixel. Now, if you want to apply to the entire image, you can do the same computation, but for each pixel of your image. So we have this 5x5 original image, and you have this 3x3 filter here. These are just examples, right? 5x5 is a very small image. But again, those values you see there in the original image, they are pixel values. And the values in the filter, they are weights. So I'm going to apply those weights to that image, and we're going to do that pixel by pixel. starting from the pixel 161 there, which is in the center of the filter, because if you start at the very first one, the 206 there, we would have this problem because the corners wouldn't be defined, right? So we have to start applying the filter at the element 1, 1 of our original matrix and not 0, 0. And then if you do that, the first pixel of the transformed image, which as you already noticed, became smaller, right? Our image was 5 by 5, but now the result of the convolution is giving us a 3 by 3 image. And this is a property of convolutions, okay? As we're going to discuss this in a minute. But let's finish this step. So the first pixel is that 161 and it becomes 178. So what I'm going to do now, the next step of the convolution is just slide my window one step to the right and do the same filter operation. Now to that 137 pixel, which is going to become 175. Again, by just what I'm doing is doing that same operation of applying those weights to the neighbors and summing all of them, and that gives me that result, okay? So I'm going to do that again for the sliding once again to the right. When I get to the end of the columns, I'm going to slide it down and go back to the beginning, okay? And I can now I'm going to run the filter for that 154 pixel, right? And hopefully you got the idea. Now I just slide the window from the left to the right, from the top to the bottom, one step at a time, both horizontally and vertically, and I get that resulting image. Okay. So this is a transformed image. Not only its values changed, or these pixels' values changed, but also its size changed. At least the way we just defined the convolution. And this is a very basic convolution. We're going to see in a minute how to deal with that problem of the corners there. It's a very simple trick. But any questions so far? This is, hopefully this is not too complicated. So one cool thing we can do with convolutions that is particularly important for computer vision is detect edges in images, right? And edges are these sharp transitions from bright to dark, or dark to bright. Right? If you have a region of the image which is very dark, and you change it all of a sudden to very bright, then it's an edge, or the opposite, right? If it's very bright and you change to very dark, that's an edge. And we can design filters that when we apply convolutions to them, we're going to detect these edges. And we can do this in many different axes. So we can do, for example, a vertical edge detector, which would detect edges that are vertical on the image. You can define it this way. It's all zeros in the all ones in the first row, all zeros in the middle, and all minus ones on the rightmost column. In the same way, we could define a horizontal edge detector by creating this filter here. And the purpose of this lecture is not to discuss how to create these filters. This would be a topic for an image processing or computer vision or classic computer vision course, because computer scientists or computer vision researchers, they have tried many of these filters over time, right? They have been studying this for a long time. So these are not random numbers that I'm picking, right? They have a meaning. So if I apply these two filters to this image, I get something like this. So here I'm detecting both vertical and horizontal edges. So as you see, I can see the silhouette of the elements of the picture. Right? And this is very useful in computer vision because for example, if I want to detect objects in an image, looking only at the shapes of these objects might simplify my problem. Right? So we can think about these filters as feature extractors. Like, if I'm dealing with object detection or object recognition and I need to find a person in an image, imagine we are building a self-driving car, you have to build this model that takes an image as input and outputs the location of a person in that image, right? So it might be easier to do that if you get the edges of this image, because then you would have the silhouette of the person highlighted for you, and that would probably blur or remove all the background that is, in this case, is more like a noise to me than the actual silhouette of the person. Anyways, you can do many things with filters, and people have studied them for a long time, okay? And they are very important in computer vision. We just saw this very simple vertical edge detector filter, but there are many other ones that have different numbers in them, and they change the images slightly differently, right? So for example, there's this very classic filter for edge detection called Sobel. There's another one called Char, and the way that you change the numbers here give you different results. And they might be better from one application than another. Right? So let me show you a demo here in the school website here, where you can apply filters to images and see the results here. So what you see when you pass your mouse over these numbers here, all these numbers are pixel values. You can't read them, but they are values from 0 to 255. This is a black and white image, and here you are highlighting the pixel on the image and the respective value there, okay? So you can kind of check what is the value of any given pixel. So, and the next, you can pick a filter, which is a 3x3 matrix, and they have here many different filters already predefined. Like you can see there, left Sobel, top Sobel, right Sobel. As I said, Sobel is an edge detector, and you can detect right edges, left edges, top edges, bottom edges, right, depending on what kind of object you're trying to recognize. Right? But let's look at the blur kernel. This is exactly that kernel, or sorry to use that word, filters are also called kernels, okay? They're the same thing. So when you see blur kernel, is also a small matrix, is exactly the same thing. So here is the blur filter, and right next to it you can see the result of the convolution. And you can actually highlight any pixel you want and see how the filter is applied, or the result of that convolution step. So remember, the convolution is the application of the filter to the entire image. When you want to highlight just one step of a convolution, you can say one convolution step, for instance. Like this is one convolution step we are seeing just there, right? It's multiplying all those weights to its respective pixels and summing all of them, and that's giving 1678, and that's the value of that pixel right there. Okay? And visually, we see from far away that, yeah, indeed, this is a blurred version of that image. Okay? But let's look at the sharpened one. This is cool as well. This makes the whole image more sharpened. Or outline. Right. Here you get the outline of the object in the image, and this is, so see how they have all these kind of like apparently random numbers, but if you look at the way they are defined, or they are disposed in the kernel, it kind of gives you some hint of how and why they do what they do. Okay, so I think next to, here you can even make a video, I guess. I'm not sure it's going to work. Yeah, it's not going to work because I'm using my camera already. But you can use your own camera and like see the filters applied to it. And here is a larger image where you can just see the same results, but in a larger image. Oh, here you can actually play with the numbers. Okay. So here it's a playground. Feel free to design your own filter. if you want. Okay. There's many of these demos online, okay? Many of these like convolution playgrounds out there. This is one that I like. So the whole idea of convolutional neural networks is to learn these filters and not design them by hand. So I don't want to come up with these weights myself. I want to design a learning process that I want to learn these weights from an image data set and a loss function. Okay? So if my goal is to detect objects in an image, I'm going to design a loss function that represents that problem. I'm going to create a data set with a bunch of images. I'm going to label where the objects are with maybe a bounding box around them. And I want my network to learn these weights for me in a way that it minimizes the loss. So at the end, I don't have to come up with these weights to process images or to solve any particular problem. Because prior to like deep learning, the whole idea or the major idea in computer vision was to design algorithms that would take images, then use filters to get features. So this would somehow generate a vector of features So this would generate a vector x, and this would go into a classic machine learning algorithm. Let's say, and this would give us a prediction, y hat. Right? And this could be a image classification problem, let's say. Like cats and dogs, right? And here you would see algorithms like SVM, or even logistic regression, something like that, right? But this part would be done beforehand. So you would first get your data, then you would define a bunch of filters by hand that somehow would give you interesting features that you could plug into your machine learning algorithms. So what I'm trying to do right now is to learn these filters and train this whole thing end to end. Before that, this step here was done, let's say this was feature engineering, we would call. So, feature engineering. And then this would be training. So they are separate steps. This would be training. So what convolutional neural networks do is they do these two processes in only one by learning these filters. Okay. So you're going to randomly initialize these filters and design a loss function. And here we're going to plug now a CNN, right? Or a convolutional neural network. And what you want to do is just do simply this. And somehow the CNN will learn the filters for us and come up with the predictions. Does it make sense, what I'm trying to do? So we can see that our weights of our network are going to be built in the filters. Before we see the dynamics of a convolutional neural network and how they work, we need to understand some ideas about convolutions a little bit more deeper. I already mentioned that when you apply convolution to an image, you get a smaller image. And here's an example, or the same example, right? We have a 5x5 image, we apply a 3x3 filter, and we get a 3x3 image. So first of all, it's important to be able to compute these sizes. It's very useful when you are designing convolutional neural networks. It's useful to know, based on the size of the filters, and I'm calling the size of the filter f, the letter f, here's the size. So 3 by 3, f is equal to 3 now. And n here means the width and height, because this is a square image, so the width and height of that image. So if I have a convolution that of a n by n image by an f by f filter, that would result in an n by f minus 1 wide image. This is the width, and same for height because it's a squared image, right? So the general rule is n minus f plus 1. Right? And you can check that math. In this case, would be 5 minus 3 plus 1. Right? That's 2 plus 1, 3. So in fact, we got a 3 by 3 image there. Okay. This is good because when you're dealing with convolutional neural networks, as you will see, we're going to have many layers of convolutions, and then you're going to have many of these transformations going on. So it's good to, it's really important or very useful to know how the transformations are going to decrease your image. So you have to, sometimes that gives you information to change your layers or something. We're going to see that happening. But more especially, and probably you can already visualize that, if I keep applying a filter to an image, that image is going to keep decreasing, and eventually it's going to become a 1 by 1 image, right? For example, if I apply this 3 by 3 filter to this transformed image here, again, it's going to become a single number, right? So that would be a 1 by 1 image, just one single pixel, right? So every time I do a convolution, I'm somehow compressing the image in less numbers, right? So to solve this problem, we're going to use what we call padding, which is a very simple idea, which just consists of adding a border of p pixels to the original image. So visually, this would be it, right? This is a padding of size 1. I'm adding a border of size 1 to the whole image. And I'm keeping the filter 3 by 3. So the original image is still 5 by 5, but now I augmented it with an extra border. Okay? And, oh, sorry. This was meant to be done later. But as you can see now, if we add this extra border to the image, then now that corner pixel starts to be more frequent in my convolution operations, right? And you can think about this padding pixel values as zeros. But what padding does is also, it helps you keeping the original size of your image. Because we haven't changed anything in the convolution definition. It's exactly the same thing. I just changed the original image, okay? So, if you have padding in your image, and you can have padding with a larger size. You can have padding of 2, 3, 5, whatever you want. You can add as many padding as you want. And we're going to control that as a hyperparameter of our model. Depending on what you are trying to achieve, you're going to have more or less padding. Okay? This is not, there's not a one single way to do this. Okay? It's just a property that we can take advantage of. Again, because now we can add padding to our images, our formula for computing the size of the output image changes a little bit. Okay? So now if I have an n by n image and an f by f filter, the resulting image or transformed image will have n plus 2p, sorry, minus f plus 1 . height and also width. It's going to be the same, right? Which in this case is height is 5, right? It's 5 plus 2 times p. P is 1 minus f. F is 3 plus 1, right? So this is 7 minus 3, 4 plus 1. So this is 5, right? So this is exactly what we got here. So by adding padding, we can maintain the size of our original image, even after applying convolution. Okay, that's the important property. Frequently, you want to find a value p that keeps the size of an n by m image. So for any image of size n by n, I want to know how much padding I need to add after convolution of a filter of size f. So I give you a filter size, right? I give you an image size, and I want to know what p do I need, what value, how much padding do I need to keep the size of my image the original size. And you just have to solve this equation, right? We just saw that this is the formula to compute the size of the transformed image. It's n plus 2p minus f plus 1. Don't worry, that's very easy to come up with that formula. You need that to be equal to n. The original size, right? We want that to be original size. So if you solve that equation, you would get this. Okay? P equals to f minus 1 over 2. This is very useful in code when you're programming convolutional neural networks. You want a layer that makes sure, you want a convolution layer that makes sure that, oh, I don't want to mess up with the original size. So I can parameterize my code and always compute the size p based on the size of the filter and the image. So here's just you don't have to memorize these formulas, okay? Don't worry about memorizing them. It's useful, and the more you work with convolutional neural networks, the more you're going to internalize these formulas. But if you don't keep working with them, you're going to probably forget, and that's fine. That's not a key point of this lecture, okay? Another variation of convolution, so we just talked about padding, which is adding a border to the image. Another very common and useful idea is to run a convolution, but not hopping or sliding the window by one step, but maybe by a larger size of a step. Right? So we call that step size stride. We've been seeing convolutions with stride of size 1, because we would slide our window one column and row at a time, but you don't have to do that. You can slide by a larger number. And here's an example, right? I'm going to run the same convolution, but now with stride 2. And that what's going to happen now is I'm going to jump from the very first corner all the end to the right. So I'm jumping 2 steps at a time. Right? I'm jumping, I was here, so I jumped 2. 1, 2. So now my matrix ended up here. And I'm going to do the same on the rows. Like now I jumped 2 steps on the rows, and also 2 on the columns. So again, the stride is the size of the jump. Let's say how much you're going to jump or slide your filter per step of the convolution. And that, as you probably imagine, also affects the size of the resulting image. Because now, with a stride of 2, and here there's no padding, okay? And you could have padding in different strides. So these are different ideas that can be put together, okay? But here it's a stride convolution without padding. And if I had this situation, a 5x5 image and a filter of 3x3, I would get a 2x2 image. Because if you just notice the animation, I had 4 convolution steps. Each of these steps would generate a pixel value, so I would get a 2 by 2 image. So by increasing the stride size, you are decreasing the size of your image more strongly. Okay? Yeah, I just defined what the stride is. And again, more formulation. Now we have padding and stride, so we can still compute the resulting size of the transformed image by this formula there. Now we have this division by S. And I'm going to need more chalk. These are very small. So right now, just to check that that's correct, n plus 2p minus f over s plus 1. And now s is the stride size. Okay, this is the stride. So let's look at this example. N is 5 plus 2p, p is 0. We don't have padding in this image. Minus f, f is 3. So all of this over s equal to 2. That's the stride size in this example. Okay, all is plus 1. So that would be 0, 5 minus 3, 2. 2 over 2, 1. 1 plus 1, 2. Okay. So again, this is very useful in code when you have to figure out. So when you're designing convolutional neural network, it's very useful to compute these sizes and to make your code more parameterized. Any questions here? Okay, so this slide answers, I think, your question, Guilherme, which is, okay, what if we had different channels in the image, right? If we have multiple channels, let's say an RGB image with red, blue, and green. Now we have that volume, right? You can think about it. You can think about an RGB image with this stack of 3 images, right? One on top of the other, right? Like this image here on the left. Now the size of this image is 5 by 5 by 3 because we have 3 channels. So if you want to apply filters to these images, we also need a 3-dimensional kernel or filter. Right? So now the number of dimensions, or the number of channels to be more precise, has to match the size, the number of channels in the image. So these numbers here, they have to be exactly the same. Okay? And the way you're going to apply this is similar, but there is an important property here. If you have an RGB image, if I apply a convolution with this filter to that image, I'm going to get a flat 3 by 3 image with only one single channel. Okay? Because the way we apply this filter is by matching the channels. So you're going to slide the channels over that image one by one. Again, here you can still have stride, you can still have padding, all the same ideas, they're still valid here, but now we have more than one channel. And we also have this cube there that represents the filter, so you're going to slide that cube that way, and that would give you a 3 by 3 image. And if you're still not convinced by that, it's good to do like this by hand, so you see like this happening. Okay. So we are almost getting to the point of seeing an actual CNN. But we've been talking about just one single filter, one of this 3 by 3 filter. But you don't have to be limited by one filter only when you're training CNNs. You can actually learn multiple filters at a time. Okay? So let's consider this filter 1 now yellow. And I'm going to apply that filter to that original image, as we just saw on the previous slide. And I can have a second filter, now orange. So what you could do then is process the image with different filters. That would give you 2 different flat images, and you can restack those 2 images to get a volume that is now 3 by 3 by 2. And the number of filters you can define yourself. when you're defining, you're going to see this in the probably next slide. When you are defining what we call a convolution hidden layer, you can pick the number of filters you want. Okay? But the depth of the filter, or the number of channels, has to match the size of the image. Okay? But yeah, now we can pick as many filters as we want, and we can apply them to the same image. And then if you had three, for example, three of these filters here, the resulting image would be 3 by 3 by 3. I could have 10 filters, it would be 3 by 3 by 10. Okay, so you would make a deeper volume at the end. Okay, I should have put animations in here. So this is how we define a convolutional hidden layer. Convolutional hidden layer is a set of filters that you see here. You have a yellow filter, an orange filter, and then dot, 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 which could be as many filters as you want until this green filter here. So you can pick the number of filters you want. This defines a hidden layer. And for each of these filters, you're going to apply you're going to convolve that image with that filter. That's going to give you a flat image, right? Each of those filters is going to give you a flat image. You're going to apply a ReLU or any activation function to that image. Sum with your bias vector, or value in this case, sorry, the bias vector will be defined here. And stack all the resulting volumes again. So if your hidden layer had 10, sorry, this should be, I'm not making this very useful. This should be NL. But basically, I'm going to apply the ReLU for each of these filter results, sum with the bias term, and stack the results back into a volume, which is my activation. The activation of a hidden convolutional layer is a volume. And the depth of this volume depends on the amount of filters you pick for that layer. And also here I'm using ReLU, but you can pick any activation function you want. But ReLUs are more common. Okay? So mathematically, we can write the convolution equation or the equations of a convolutional layer very similar to the MLP. So you can say that Z1 is these results, these partial images here, which we get by convolving the image X. So now our image is here. Image X is multiplied on the left, is a little bit different from what you've been seeing here, but now the X is on the right, and the filter is the W matrix. Okay? So that W1 there is my set of filters. And I'm going to convolve those filters with that image X, sum with a vector B. See here, B1, B2, this should be BNL, right? Not B3 here. There we go. And then we apply a ReLU to the Z1. Z1 is the linear part of our operation here, of our convolutional hidden layer. And then we have the ReLU or any activation function to have a nonlinearity. Okay? So if you think about convolutions, convolution is still like sums and multiplications, right? So it's still like, convolutions are still a weighted sum in a matrix form, right? So we still need those nonlinearities. So we still need an activation function, which can be a ReLU or any other one. So here is our first full convolutional neural network. It's still not using all features of the modern CNNs, but we're quite almost there, okay? Right now, what you see here is, when you see these blocks, right, or these cubes, they represent the activations. So the first activation, A0, is the input image, right? So that's X, that's the image itself. So let's imagine we have a 39 by 39 by 3 input image. So that's our first activation, quote unquote. That's our input, right? So here I have some notation for us, because that's normally how we analyze convolutional neural networks. If you look at a CNN paper, you would see an image like this at some point. So it's a diagram of the network showing these volumes and having some annotations on these volumes describing their sizes or what operations they're doing. So, and you're going to see some numbers like this around them. So if my input is 39 by 39 by 3, first thing I know is that the size of my input layer N0 is equal to 39, because that's the size of the image, okay? And then let's assume that here, so this arrow, first arrow here, represents one convolution layer. And in this convolution layer, I have a filter size of f equals to 3, right? I have a stride size of 1, padding of 0, and here 10, so N1, remember from previous slide, this is the number of filters in this layer. So I have 10 filters, no padding, stride of size 1, so I'm going to do the convolution one step at a time, and filter size 3. So what you should be able to imagine at this point is that this arrow here is applying a filter that is 3 by 3, and I have 10 of them because of this. So I have, and each of them has depth 3 actually. So I have 10 of these filters. They are 3 by 3 by 3. And I'm going to apply them with a stride of 1. So I'm going to just move this filter one step at a time. And this image, I'm not going to apply any padding to this image. And that's it, 10 filters. So remember from that formula we got, I'm going to put it on the board real quick. So by using this formula and this configuration of convolutional layer, I can compute that the activation of this layer is going to be 37 by 37 by 10. So let's think about this. N is 39. 2 times P. P is 0, right? Minus F. F is 3. Divided by S, which is 1. So here's 1, fine. Okay, this is 0, 29 minus 3 plus 1. That's exactly 37, right? So this is going to be a 37 by 37 by 10. Why 10? Because I have 10 filters. Remember, we stack the output of each filter to form the activation volume. So this 10 that you see here comes from this 10. The same way that this 20 you see here comes from this 20 here. And this 40 that you see here comes from this 40 here. Okay? And the sizes you can compute using this formula. Okay? And this is how a CNN plays out. You're going to keep changing this volume. And at the very end, so this should be flattened, right? So you want to take this volume and flatten all of its elements to generate a feature vector. And then we pick that feature vector, and from now on, then we use a multi-layer perceptron. at the very end of the day, you want to do a computer vision task. You want to classify cats and dogs or something. So to actually get a prediction, you need this, to add at the very end of your CNN, you need to add fully connected neurons. They are going to give you a prediction. So you can think of a CNN as a feature extractor that is going to give you a vector at the end. But this vector was computed over a series of convolution layers, okay? We can get back to this slide next lecture. We're going to still talk about CNNs next lecture. So you can review these ideas, and we will. So for instance here, sorry, I forgot to mention, so this number, 1,960, right? It is defined from this, for flattening this whole thing here, 7 by 7 by 40, okay? So this is the point. I'm going to stop here, okay? So how many parameters does a layer with 10 filters that are 3 by 3 have? Let's think about this. So I have 10 filters that are 3 by 3 by 3. Let's do this slowly. How many weights I have in each filter? 3 by 3 by 3, right? So each of them, this has 27, this has 27. So I have 10 times 27, right? Plus 1 because of bias, okay? So I have 28 times 10 weights. These are 280 parameters for one layer. And before we had billions, remember? 3 billion parameters. And what is the most important part here, this doesn't depend on the size of the image. It only depends on the number of channels, right? So the number of channels typically don't grow. We're normally dealing with RGB images, so there are 3 channels deep, right? But the width and height of the images changes a lot. But so the number of parameters don't depend, the size of the filter, the F value doesn't depend on the width and height of the image. So now this value is not proportional to the width and height of the image. This is what we wanted to achieve at the very end. And we also get other properties that are really nice because we are processing the image with these filters, and we are sharing it's cool here, we are sharing these 27 parameters, or we are sharing these 280 parameters across multiple images. So it's really nice, and the dynamics of the convolution really help us learning computer vision tasks. But let's leave the rest for next week. And yeah, thank you. I can take any other questions right now.